I don't remember this. You're good, just as much sure keeps getting hot today. You must be heading towards the end.
This filming, so.
Yesterday was one line. Yesterday, I struggled. I didn't get to y'all's test because I struggled writing into the comments. I couldn't put down for more than about 5-10 minutes before I was like, and then I'd have to wait 30 minutes. So it's taken me a long time to write one exam. Almost. I know, and it's brutal.
Yes.
But I'll stay indoors. I'll be in. That'll help. I won't have to be out here. Good morning.
Services that is so cool. It's if I had I would not be.
Guess I could do that for folks if they're interested. Let's see. Let me go back to my Zoom. I don't know if people can see that or not. If you're wanting to log into Zoom, and that way you have it on your computer, I don't know if you can read this, but that is the links. Or you can just type in. 2939. If you'll need to log into Zoom, you can do it that way. It's just, I will say, if you do log into Zoom, please make sure your sound's off so that you don't have an echo. I don't want to hear my own voice back. I hate my voice. Okay, okay. We'll get this going. And I need to write some notes on the board. Okay, so to begin with, just a couple of quick announcements. I have not gotten to your lab because this weather is causing me a lot of problems. All the incoming rains and everything are or your exams. So I will be working on those this weekend and hopefully I'll be able to have those to you on Tuesday, with your grades posted prior to Tuesday. Second announcement I want to make is today's lab is going to be a Manion 103 since it's a lecture. I will try to put all of the lectures in Manion 103. That way it just makes your life a lot easier and you're not as uncomfortable sitting there for the length of time. Your hands are going to be uncomfortable, but I can at least make sure you're not uncomfortable. Now, if you want to log into Zoom, as long as you turn off your sound, you can always log into Zoom because I know sometimes it's easier, especially in the back, to be able to see what's going on if you're in Zoom. So I've got the information up here that is in there for the password and the code and all that jazz. So hopefully you can log in and if you so desire. I always use the same Zoom account unless somebody else starts sneaking in and causing me havoc, and then I'll change it. But otherwise, I like to just use the same Zoom account all year long. Any questions? Yes.
What do we need to do to like prepare for that?
Absolutely zilch. Just come with pen, pencil, paper, computer, whatever, but it's just taking notes. Lab lectures are just notes, and doing what we do in class. Just it basically the reason I have a few lab lectures throughout the semester is if I didn't, I would have to go faster in class. This way, I can slow it down a little bit. Maybe not a lot, but a little bit.
Will we still be out at 5:20?
Huh?
I said, will we still be out at 5:20?
Oh yeah, you'll probably be out earlier. I don't know how much earlier though. So you'll probably get out early because it's going to be very hard for me to talk for 2 hours and 20 to 40 minutes.
That'd be crazy.
I can't do it. So usually about an hour and a half, hour and 45 minutes is the maximum I can go. I will say bring drinks, food. Also, you will get a 10-minute break, 5 to 10 minute break in the lab because it's hard to sit for that long too. So, any other questions for me? Okay.
I there one.
Yes.
About the email you sent yesterday about the homework, does that mean that the homework that was gonna be due yesterday is next, or yesterday is gonna be due on Monday with the other one?
Yes, so what I'm gonna do is I'm gonna create one homework assignment that says homework blah and blah. And it's gonna be out of 10 points instead of out of 5.
Okay, cause I was looking up like, am I missing something?
No, it's my fault. Trying to get back from DC and the trip I had to take, it's just, I'm not catching up well.
What about the quiz? Like, is that posted instead of it's to be assigned today?
I will get it posted as soon as I get back to my office. That one is a lot faster to post. So both it and the homework, it will get posted today. I will give you actually until tomorrow evening to finish the quiz. Because I'm gonna be a little late getting it going. So I gotta go in and do a lot of active work today. Other questions? Okay. Then we are gonna go ahead and get started. Let me clear out everything. Available. Okie dokie. So on Tuesday, trying to remember, oh crumb, what day it is. On Tuesday, we started talking about the science that is leading up to us understanding the electron cloud in particular. And so that is where we're going to pick up today, is with that information. So on Tuesday, I talked to you about the photoelectric effect. The photoelectric effect is basically, they figured out they had to have a very specific energy in order to get an electron to move out of the atom and start flowing to make electricity. I also mentioned the atomic spectra. Unlike what was expected, which is a complete rainbow effect, we got very distinct lines when we took a hydrogen lamp and we shined the light through a prism. You got very distinct lines. Now, taking that information, Niels Bohr developed the Bohr model of an atom. And basically with the Bohr model of an atom, you have your nucleus. And around that nucleus, he said that the electron orbits around the nucleus. He called the first layer around the nucleus 1, and then he moved out from there. And I know my layers are not exactly even, but that's okay. Now, why did this model get generated? Okay, let's go back to the photoelectric effect. And let's say we have an electron right here by the nucleus. First thing you've got to understand is that there's an attraction between that electron and that nucleus, because we're talking about the protons in the nucleus, which are positively charged, and the electron in the cloud, which is negatively charged. And just like any magnet, they're going to be attracted to one another. So when we had our incident beam come in, and it strikes that electron, for the photoelectric effect, basically what had to happen is you had to have enough energy to break that attraction. But more than that, if this electron is in the second level, there is still an attraction. Even if the electron is in the second level, there's still an attraction to the nucleus. You have to break that. Even if the electron is in the third layer, there's still going to be an attraction. You got to break it. In other words, it has, in order to get this electron to flow out of the atom, we have to break every single, we have to break the attraction sufficiently so that that electron completely leaves the atom. So that you can have that free flowing electron that is necessary for the photoelectric effect. So again, it had to be the correct amount of energy, because if you only had some energy, all you did was move the electron to another layer. But that wasn't sufficient. You had to have the right amount of energy in order to completely take that electron and remove it from all layers of the atom. That's the photoelectric effect. That's why the incident beam had to be of a very specific energy, is because it had to be enough to get that electron out of all layers of the atom. Now, let's talk about how the atomic spectra comes into play. First of all, with an atomic spectra, you're still going to have that incident beam coming in. But now that incident beam is of a specific energy to take this electron and excite the electron, but not get it to be completely removed. So with atomic spectra, we're not removing the electron. All we're doing is exciting it. And so we can excite it to the outermost layer. Whoops, I didn't get that right. And when that electron falls back to level 2 to stay, it gives off a line of color. That electron could be excited to a different layer. It could be excited to the 5th layer instead. Well, when that electron falls back to the 2nd layer, it's going to give off some light. That electron could be excited to the 4th layer. And when it falls back, it's going to give off light of a specific color when it falls back to 2. Or it can be excited to the 3rd layer. And when that one falls back, again, you get a specific color. So the atomic spectra arises from an electron being excited to an outer shell, which is what we call these things, an outer orbit, if you will. And when that electron relaxes, it falls back to level 2. And when it falls back to level 2, orbit 2, you get a very specific color that is generated, and that color is relative to the layer it falls from. Questions about, so in other words, it's not the excitation that causes the color. It's the relaxation. Excitation means it goes to a higher level. Relaxation means that it falls back to a lower level. In this specific case, you'll notice I always had it fall to 2. When it falls to level 2, that's when we get visible light that you can see. You had your hand up, Amy.
That was my question.
Okay. It can fall to other levels. It doesn't have to fall just to level 2. But again, when the final N equals 2, you get visible light. But it can fall to other level, it can relax to other levels. If the final level, for example, is equal to 3, you're going to get infrared light, which you cannot see. And if the final level equals 1, then you're going to get ultraviolet light, which again, you cannot see. So the reason I just used 2 is because we were talking about the atomic spectra you could see. And that means it had to fall in the visible region. Questions about that? Yes.
So are you saying like if it goes up to 5, that's the color it is, or like?
No. Okay, so if it goes from 5, if it relaxes, again, it's not the excitation that causes the color. It's the relaxation that causes the color. And when it relaxes from 5 down to 2, that's when you're going to get some color you could see. Other questions?
Depending on if it like goes to like 3, 4, 5, 6, does that like change like the color? Like if it's red? It's
Yes. So it's red, even though this looks red. I don't know why, because I chose a purple, but it is a red color when it goes from 3 down to 2. It tends to be a teal color when it goes from 4 to 2. And it tends to actually, this should have been purple. It should be 2 purple colors when it goes from 5 to 2 or 6 to 2. So the color is directly related to where it's going from down to 2. The visible colors. So right now, folks, you will notice that other than the photoelectric effect, where I just described it as pretty much any atom giving off the electron, when I showed you the atomic spectra on Tuesday, and with this Bohr model, I've been talking about hydrogen. I've been talking about hydrogen because it's the simplest. It has one proton and one electron. Now, with the atomic spectra of hydrogen and the Bohr model of hydrogen, two individuals came in and developed an equation. And that equation allowed us to predict this starting number and where we ended up. And that equation is the Rydberg-Balmer equation. So the two people that found it were Rydberg and Balmer. They pretty much found it at the same time. And the equation is 1 over lambda is equal to R times 1 over n sub f squared minus 1 over n sub I squared. In this equation, lambda is, as we've been describing it, which is the wavelength. R is known as the Rydberg constant. And the constant you want to use is going to be directly related to the unit you want to use for the wavelength. Because, for instance, R can equal 1.097 times 10 to the minus 2 per nanometer. If you want to have your wavelength in nanometers. In other words, it's a dictator. It's a constant. Constants are dictators. But we can also use R is equal to 1.097 times 10 to the 7 per meter if we want our wavelength in meters. So it's really dependent upon which variation of wavelength you're going to use. Now, for me, I find this first constant to be the most useful because the instrument you're going to be looking at in lab is going to give you your it's going to give the wavelengths of light in nanometers. So it makes sense to use the constant for nanometers. But on active, some of the active questions talk about the Rydberg constant in meters. So pay attention is what I'm trying to say. The R value is your dictator. Now, the rest of it, n sub f is going to be the final orbit that the electron relaxes to. And n sub I is going to be the initial orbit that the electron relaxes from. And I do want to point out, I'm using this term relaxes, meaning it's wherever it starts is way out here and it relaxes. So in other words, I'm not talking about where it was excited from, because it's always going to be excited from orbit 1. But I'm talking about where it relaxes from. So I'm using the terms carefully to distinguish. So let's just look at an example. Visible light of 410 nanometers was given off when an electron of hydrogen relaxed. What is the N sub F, the N sub I, the frequency, and the energy of the electron? Okay. Folks, I'm seeing, so let's talk about equations. N sub F and N sub I tell me I'm going to need the Rydberg-Balmer. Frequency tells me I'm going to need to use C is equal to frequency times the wavelength. And energy means I'm going to either need energy is equal to H times the frequency, or energy equals HC over lambda. Okay, let's begin though with the Rydberg-Balmer. Which is 1 over lambda is equal to R times 1 over N sub F squared minus 1 over N sub I squared. The lambda that I was given is 410 nanometers. That is in the equation. R is my constant. The R I'm going to choose has nanometers. That way I don't have to change my unit of wavelength at this time. So that's 1.097 times 10 to the minus 2 per nanometer. N sub F, folks, the N sub F was described right here, even though I didn't state it. It has to be energy level 2 or orbit 2, because I said it was visible light. So really what I'm looking for is N sub I. Okay. So I'm going to do this the slow way the first time, and then the second time I will speed it up. And I'm going to walk you through the algebra that I use. If you're really good with algebra, I apologize up front, but I know a lot of people struggle with this equation. I've seen it year after year after year. So First thing I'm gonna do is simplify a lot of this stuff. So I simplified the fractions. The next thing I'm going to do is I'm going to divide the left side by the R value. And that comes out 0.222336 is equal to 0.25 minus 1 over n sub I squared. The next thing I will do is subtract 0.25 from both sides, or whatever that 1 over n sub f squared was. And when I do that, I get a negative 0.027664 is equal to a negative 1 over n sub I squared. I multiply equation through by a negative 1. So that I get 0.027664 is equal to 1 over n sub I squared. Finally, I use I use the inverse button. On the calculator, which is x to the negative 1. Oh, it messed up on me. Give me a sec so I can get back to it. And you get 36 is equal to n sub I squared. And then I take the square root. And when you do so, you get n sub I equals 6. And yes, like I said, if you're really great with algebra, you probably didn't need all that. This is what I do, this is what I do, this is what I do. But the main reason I'm showing you that, and I'll only do it once for you, is because of the fact that I've seen it too many times where students struggle with that. So. Yes. N does not, because it's just telling you where is the electron. the question is, how did I know NSBF was 2? Because of visible light. And if you go back up here, when I was talking about the orbits, right here, that's how I knew it was a 2
So it's always gonna be 10.
for visible light. Yes. Questions so far? Okay, so we now know, so we've got 2 of our pieces of information. Now we're gonna get the rest, which is, we're gonna use the equations you've been using. So we know that C is equal to the wavelength times the frequency. C is a constant. It is equal to 3.0 times 10 to the 8 meters per second. We know the wavelength here was equal to 410 nanometers, because the speed of light is a constant. It is a dictator. So we're going to convert these nanometers into meters. And we actually, it's 4.10 times 10 to the minus 7 meters. And now we can look for our frequency. So C over the wavelength is going to give us our frequency. So 3.0 times 10 to the 8 meters per second divided by 4.10 times 10 to the minus 7 meters is going to give us our frequency. And you get a value for your frequency of 7.32 times 10 to the 14. And that's going to probably, that will have the unit of seconds, or you can report it as 7.32 times 10 to the 14 hertz. The last thing we were asked to deal with is energy. Well, energy is equal to H times the frequency, or you can use energy is equal to HC over lambda. I don't care which, you'll get the same answer. I'm going to use the first one since the frequency is staring me in the face. H is equal to 6.626 times 10 to the negative 34 joule seconds. And we just calculated our frequency to be equal to 7.32 times 10 to the 14 per second. So now we can get our energy. Energy is going to equal 6.626 times 10 to the minus 34 joule seconds times the frequency of 7.32 times 10 to the 14 per second. So our energy comes out to be equal to 4.85 times 10 to the minus 19 joules. So to answer all of our questions, our N sub F was equal to 2. The N sub I was equal to 6. The frequency was equal to 7.32 times 10 to the 14 hertz. And the energy was equal to 4.85 times 10 to the negative 19 joules. Questions? I'm gonna let you work on one and I will come around and help. Started on this side. I don't know about half. Okay. So it has to go down this way. Fix that in. Everybody's fine. Else that did not sign in. Okay, how's it going? With the Rydberg-Balmer equation, you should have found that the electron fell from energy level 4 down to energy level 3. It had to be a 3 because in the background information I said infrared light. And infrared is N sub F is equal to 3. So with the Rydberg-Balmer equation, putting in N sub F is equal to 3, I determined that N sub I had to be 4, so it relaxed from energy level 4 or orbit 4 down to orbit 3. Using the wavelength into the speed of light equation, the first thing I realized is that the speed of light constant is a dictator, so I converted the wavelength into nanometers. I'm sorry, from nanometers into meters. And then I plugged it into the speed of light equation to get the frequency to be 1.6 times 10 to the 14 per second, or 1.6 times 10 to the 14 hertz. And then for the energy, I took that frequency that I just determined and plugged it into the equation. Energy is equal to H times the frequency. H is a constant, it's constant. It's 6.626 times 10 to the minus 34 joules times seconds, times the frequency of 1.6 times 10 to the 14 per second. And that gave you an answer of 1.06 times 10 to the minus 19 joules. Yes. Okay, to get to the frequency, you have the wavelength in the equation. We know it's the wavelength that we have because of the unit being in meters. So I use the speed of light equation. C is equal to the wavelength times the frequency. The C is a constant. It is always 3.0 times 10 to the 8 meters per second for our purposes. But it is, because it is a constant, it is also a dictator. So it said that the wavelength had to be in meters. So I took the 1875 nanometers and I converted that into meters. And that comes out to be 1.875 times 10 to the negative 6 meters. Plugging that into the equation is how I got to the frequency.
Can you explain the guide? 0.06.
So to get from there to the other, I took, first of all, I don't usually write out all the steps. So I would have taken 1 divided by the 1875. And then I would have taken that answer and divided it by 1.057 times 10 to the minus 2. And that's how I would have gotten the 0.048 here. The other part is the 0.1111 comes from 1 divided by 9. So that, and then you get this number, you should have taken that, subtracted out to 0.111. Yes. When you subtract out 0.1111 from maybe from 0.048, it comes out to be a negative number. Because I'm subtracting 0.1111 from both sides of the equation. So I subtract it from this side, I also have to subtract it from the other side. Other questions?
Just like when you got the 16, do we just round to the whole number?
Yes. For our purposes, because as long as the molecule is or as long as the element is hydrogen, you will get a whole number. If the element is anything but hydrogen, the Rydberg-Balmer equation fails. If the element is anything but hydrogen, the Rydberg-Balmer equation is going to fail. Can anybody tell me why it may fail?
Too many protons.
You got a bunch of protons. And more than one electron. The Rydberg-Balmer equation works because it's a one-to-one interaction. One proton to one electron interaction. But if you get in there and get multiple protons and multiple electrons, let's just look at what that would do. So if I were to go in here, here's my protons. Well, I'm going to separate them out further because I want to show you everything going on. So let's just take helium. It has 2 protons in the nucleus. And out here it has electrons, but it has 2 electrons. Now, these electrons are in constant motion. So part of the problem is number one, you're going to have the electron attracted to that proton. You're going to have the electron attracted to that proton. But you're also going to have those protons repulsing one another. And because electrons are in constant motion, there's going to be times where those 2 electrons are next to one another, and you're going to have repulsion here as well. So the problem with the Bohr model and the problem with the Rydberg-Balmer equation is it's only good for hydrogen. It's only good for hydrogen because it only takes into account one interaction. But when you get more protons and more electrons into the system, you've got a lot more than just one interaction. And the Rydberg-Balmer fails. And technically the Bohr model fails at that point. So that's why we only use the Rydberg-Balmer for the minimal, which is that of hydrogen. But you know what? It was this theory, all these theories though, that allowed us to start developing the electron structure. Yeah, it fails after you go past hydrogen. But the Bohr model was our first idea of what that electron cloud, that electronic structure looked like. So let's talk about what happened. First of all, if we're talking about the photoelectric effect, using the model that I just described, if you're talking about the atomic spectra, using the model I just described, if you're talking about the Bohr atom, Bohr model, if you're talking about the Rydberg-Balmer equation, all of these are looking at an electron as a particle. But electrons have a wave particle duality. And we have not even considered the wave portion. So let's talk about the wave portion of this wave particle duality. First of all, if we're talking about a wave, the first thing we can find is that the wavelength is inversely proportional to momentum. Folks, that makes sense. If you think about it, remember our wavelength is this distance that it travels from one peak to the next peak, or from one trough to the next trough. If I am going slow, I have a very slow momentum. My wavelength is going to be long. But if I'm going very, very fast, the wavelength is going to be fast. So they're inversely proportional. I mean, the wavelength is going to be short. So they're inversely proportional. To go fast, you're going to have a much shorter wavelength. So wavelength is inversely proportional to momentum. Now, here's where we run into problems. So it does act as a wave, but here's where we run into problems. And that is the way we get into this wave particle duality. If you can see the particle, in order to define the particle, that means it's not going anywhere. If it's kind of like a car, if I can see every little detail about that car, the chrome or the steel, any little scratches, any little dents, that car cannot be moving. But a wave means that it's in motion. What are you doing? Whereas if I see it as a wave, then it's in motion. And I can't see it as a particle. Does this make sense? If it's in motion, you can't see every little detail. So you can't see the particle. But if you can see the particle in every little detail, then it can't be in motion. This concept is what led to the Heisenberg uncertainty principle. Yes.
We're talking
about the like part without like moving or not moving? Are we still talking about the part like the electron jumping from orbit to orbit?
So if we can see where it's sitting, it's not giving off light, right? So if I can see that it's in that sixth level, it has to be stationary. And it's not dropping at that point to give off the light. So if I can see the light, it had to be in motion, so I couldn't see the actual electron.
So the light doesn't come from like the fire, or it comes from like it actually falling down?
Correct. Correct. Heisenberg took and developed all this into the Heisenberg uncertainty principle, and then all of this science, all of this led to the Schrodinger equation. The Schrodinger equation predicts, that's all it does. It predicts the most likely place where the electron will reside. It's a prediction and prediction only. Now, to solve the Schrodinger equation, you need calculus. Because it includes double and triple integrals. Now you'll be happy to know I'm not going to teach you calculus. I'm not going to make you solve for the Schrodinger equation. First of all, most chemists to this day can only solve the Schrodinger equation by hand for the element hydrogen. Once you get to helium, it gets too complicated, and so you got to have a computer. So we're not solving the Schrodinger equation, but I'm going to tell you that the Schrodinger equation describes the location of the electron, or the probable location. If I can spell today, I would love it. With 3 values. There's actually a 4th one. And these values are called quantum numbers. I'm just going to introduce the terms now, and we will rediscuss these terms and get into it in lots of detail at lab today. And then we're going to see how these individual terms are embedded into the electron configuration in the periodic table during lab. The first term is known as the principal quantum number. Which is represented with a lowercase n. It describes how far from the nucleus an electron resides. You have the angular momentum quantum number. Which is represented with a lowercase l. And the angular momentum quantum number describes the predicted density diagram where the electron is found. We will call this in greater detail as the orbital shape. Or the subshell. Let's see. Principal, angular momentum. Why can't I remember my third quantum number today? The last one is represented by an M sub L. And it describes the axis. Thank you. For some reason, I could not come up with it today. I was going to get there, but the XYZ axis, the electron resides on. There is a fourth one, which we'll discuss, that is important once you get to helium. But for now, we'll stop with those three. Thank you. I kept wanting to say spin, and I'm like, no. Leave it like that. Okay, so I have two questions, or I do have a question for you. Because I feel like you've seen both sides of the coin now. This is not related to the topic. We're going to get into this topic more in lab time. By the way, folks, if you're free from 10:50 to 1:30 or 2:40 to 5:20, you can come to either lab when it's a lecture. It's only when it is a actual lab that you can only come to that time frame. But you can come to either one if you're free during either time. So you've actually seen me do two different lecture styles to a large extent in the short time we've been together, and I need to know preferences. So I need feedback. The first one I expected you to watch, and I still will expect you to watch the videos because I'm not going over everything in the videos most of the time. But in the first one, I expected you to watch the videos, and then we pretty much did nothing but problems with very little lecture other than me using Mentimeter to ask you questions. The second is me actually doing a little bit more lecturing and working a few less problems. I need feedback on preferences because this is your class, not mine. And I will do whichever is best for you.
I like this one, I like the, a little bit more lecture.
I'm seeing lots of head shaking that this is the preferable way. Okay. I will continue to do more lecturing, but I wanted it to be up to you. This is your class. I'm just up here trying to get the information to you, but it's still your class and how you learn best. And I will do what is required of me. Like I said, watching the videos will still be important because there's going to be some things that are in there, but also it's important because even if I do lecture, it kind of solidifies the knowledge because you kind of hear it twice. So, okay, well, I will see everybody in lab. I will be zooming in lab too.
When did you say that first lab was?
10:50 to 1:30.